Integrals of vector-valued functions. Consider the vector-valued function r of t, which equals f of t, comma g of t, comma of h of t. Then the integral from a to b of r of t dt equals the integral of each piece separately. So a to b of f of t dt, and I will change the notation using this other notation I, plus the integral from a to b of g of t dt j, plus the integral from a to b of h of t dt k. Don't get lost in all the notation. You simply integrate each component separately. For example, consider r prime of t equals 2 cosine of t I plus sine t j plus 2t k. And we want to evaluate the integral from 0 to pi over 2 of r prime of t dt. So it's simply the integral of the first piece, so the integral 2 cosine of t is 2 sine of t, and then from 0 to pi over 2, and the I is the I component, plus the integral of sine of t, which is negative cosine of t, from 0 to pi over 2, and then j, plus the integral of 2t, which is simply t squared from 0 to pi over 2, and then k. So we can do each of these pieces separately. So 2 times the sine of pi over 2 is 2 times 1 minus 2 times the sine of 0, or 0. So we have 2 minus 0i. And then we have minus, I'll factor out the negative sign, and plug in cosine of pi over 2 gives us 0, minus plug in the bottom limit, cosine of 0, which is 1, j, plus plug in the top limit, pi over 2, so pi squared over 4, minus plug in the lower limit, 0, k. And if we were to simplify everything, we get 2i plus j plus pi squared over 4. Okay, so if you understand integral rules, you understand how to do these things. You just have to do multiple of them usually. But let's do one more example. Let big R of t be an antiderivative of little r of t. Well, little r of t is 3t squared minus 2t, comma, 2 cosine 2t, comma, 1 over t. And then big R of 1 is a vector 2, negative 1, 1. We want to evaluate big R of pi over 6. So from the fundamental theorem of calculus, we know that big R of pi over 6 is going to be big R of 1 plus the integral from 1 to pi over 6 of little r of t dt. So don't forget the starting value that we need when we're finding an n value, r of pi over 6. So let's just find the integral portion back here on its own. So let's integrate from 1 to pi over 6 of r of t dt, which is going to be the integral of the x part, or the f of t is what we've been calling it. So we're going to have t cubed minus t squared from 1 to pi over 6, and that'll be the I. And let's integrate this next part, the y part, or the h part as we've been calling it. The integral 2 cosine of 2t is going to be the sine of 2t. again from 1 to pi over 6. And that's the j component. And then integrate the last part, the h or the z part, and that's going to be the natural log of t. I don't need absolute values because of my limits up there, my bounds, for 1 to pi over 6. Let's start filling some of these things in. So we have t cubed at pi over 6, at t equals pi over 6. So we're going to get pi cubed over 216 minus pi squared over 36. That's the top limit, minus plug in the bottom limit is going to give us 1 minus 1. There's our I. Plus, now we do the next part, the j part. The sine of 2 pi over 6, or the sine of pi over 3, is going to be root 3 over 2, minus, plug in the lower limit, gives us the sine of 2. It is what it is, j. And finally, the k part. We get the natural log of t at t equals pi over 6, gives us, of course, the natural log of pi over 6, minus the natural log of 1, which is 0. Okay. So this is not our answer. This is simply this back integral part. But don't forget, we need to add in our starting vector, r of 1. So r, that is big R of pi over 6, is going to be this first piece, and I'll make this part 0, plus the initial x, or the initial f of t. So we have 2 plus pi cubed over 216 minus pi squared over 36 I. And then we have this next piece. Don't forget our starting y or starting g. So negative 1 plus root 3 over 2 minus sine of 2 j. And then our starting z or h part, 1 plus natural log of pi over 6. Okay. And that's big R of pi over 6.